Okay, so let's start here with the second part. So as I said, this is a very important part, an understanding of this radiated field from antennas. And that is nothing that we do when we produce our antennas. This is how the world is in some ways. So you always will have this case where you transmit from an antenna, typically a dipole, far away of that. So we're talking only now about far field properties of the antenna. Near field can actually be quite different, but we are far away from these ones. Then the power is propagating away from your antenna, and your electric field and magnetic fields are perpendicular to this direction. And think about your right-hand rule there. Put the thumb in the direction away from your antenna. That's the direction of propagation. Then your two under fingers are in the E and H directions. So this is a property we have. And now we have a machinery to actually determine the radiated field from our antennas. And now you have an understanding of this formula. So the formula that I've written up here should not be something that you just open the formula sheet and you say, oh, that's the formula I use. I'm learning how to use it, but I don't know what it is. No, you should understand what that formula says. You should know what the background is of that formula, because then you can interpret it, you understand it, which means you will basically remember it. You don't need the formula sheet for it. So if we do that, then we can then write up our electric field here, our magnetic field here, as this part that I denote with the radiation vector and this symbol that comes down here, which says it is the part that is perpendicular to the r hat direction, the orthogonal part of that one. The first thing here is a phase factor and a decay 1 over r. So we just change that the phase is changing, and if you want to have the power, of course, you take the absolute value of this one, it disappears. So it doesn't matter when we look at properties of directivity or gain. And this says how the electric field then decays, and this is a scaling factor that stands in front of it. And that's just because we use the F here. And in many cases, we write that now in two new coordinates, which I will come back to very soon and say what they are. And that comes in from this case that they are perpendicular to this radial direction that goes away, which means that they will point in two other directions, which are on the tangents to those ones. So they're perpendicular to this radial direction. I call them here theta hat and phi hat. And I come back to those soon. And you see the magnetic field have the same shape, but with a minus sign instead. And the pointing vector then, by taking the cross product between those two, is only this perpendicular part of the radiation vector squared. It points in the r hat direction. And this is related here to the radiation intensity. And again here, I know probably I mixed this a few times. Oh, let's see here. This should then be U in this notation. And I wrote it before. Sometimes I call this P, sometimes I call it U. I'm trying to change it to U's, but I probably missed it here. So that is radiation intensity. And the radiation intensity then says how the power is in different directions. How is the power distributed in different directions? The R2 says that it decays as the distance squared. And the R hat here says that the power is propagating away from your transmitting antenna. And R hat can point any direction, but it's always away from your source. So these are the things that we have in these antennas. Yeah, and that was the interpretation as I exactly just said there. So now we're going to do this. And what we're going to do is that we're going to have this from an antenna. We're going to do it in spherical coordinates. And as I mentioned before, you all know spherical coordinates, but we should of course be better of interpreting them. So now we have to interpret this in spherical coordinates. And spherical coordinates you all have had in your basic analysis courses. So what that means is that we take our x, y, and z coordinates. So where my x, y, and z. Typically think about x and y is in the horizontal plane, z pointing up. And then you add two angles into these ones. So I take my theta angle, it's called the polar angle. It's measured from the z axis, from top and down. And I have my phi that goes from the x out to y. That typically you can call maybe polar coordinates. And you can see if you do the 2D part, that is the part that sits there. And then the elevation part, theta comes in, that is sine theta part, or in the z component cosine theta. Those are the parts that we have. This is our spherical coordinates. And that's how we describe something then. We say that antenna radiates in this direction. We say what is theta and what is phi. Because we have to say how it radiates away from the center of these ones. And of course, also in this, we need to add things now. Because what we knew or known is that the electric field also points in a certain direction. So I need to add directions. And then we add 3 directions of this, which are the one I'm going to describe now. So I have one coordinate here, r hat. I have one that is theta hat, and one is phi hat. And those are the coordinates that points in the direction where these coordinates increases. So if I have r hat, then it goes straight out, because if you increase the radial component, it goes further away. Theta points down because theta goes from here and out. And if I increase that, theta continues down. And phi goes around in xy plane. I will talk about those quite a lot now. And those are the one where we say that electric and magnetic fields are in. So they will point in these 2 different coordinates, which means that when I determine the radiated field from a dipole, I have to write it in some coordinates to say what the radiated field is. And that's where I actually need these coordinates to do that. So if I move it, as I said, I increase theta, this just continues down. So they can continue and point in any direction. And what do they mean? How do we think about this? Because it's important that you don't get formulas to this. You should get some intuition. So right now, you know, we are in Lund, so we are like down there in some ways, southern part of Sweden. So if you think about the Earth, it's basically a sphere. And then you can now compare what we do with antennas with what you have on positions and directions on Earth. And when we do that comparison, we take our antenna here. I don't put it on the surface of the Earth. I put my antenna in the center of the Earth. So the antenna here really sits in the center, far in somewhere here. And then it can radiate out in some direction here. And I can say, okay, what is the field here? What is the field here? What is the field here? So that means that you can think that you sit anywhere on Earth and you measure how much power do you receive. And then you plot how much power you have received compared to the position where you are. And that is your radiation pattern of your antenna. So that's what we have. And then if we do that to describe the coordinate system, so we understand the coordinate systems, we think what we do on Earth. We need to say, where am I and in what direction am I going? Those are the same thing that we have for antennas. So for antennas, we say the radiation intensity, it depends on the theta and phi angles, so on the direction where they're going, but it also depends on the polarization. And the polarization here corresponds to the directions. And in these cases, the radiation intensity depends on the basically positions. So I measure a certain power at the position, but I don't know in what direction it's pointing. That comes from the polarization. So now we can try to make a picture of this, what it means. And doing that, think what you do on Earth. Again, on Earth, you have something called latitude and longitude. I hope you all have heard about this. And if you have not, you've seen the globe, you know what it looks like. So latitude is what's measured here between the North and South Pole. So the North Pole is called 90 degrees, the South Pole minus 90 degrees. So it depends how far north you are, basically. The longitude is going around these ones, and it starts along this line, and then it measures the angles around these ones. So what is the angular change around these ones? The 0 is in Greenwich, outside London, and then it can go between minus 180 degrees west and plus 100 degrees east. So that is how we say, where are you on Earth? So for example, you are in Lund, you have some certain coordinates. As I say here, we are then at 55 degrees north and 13 degrees east. That's where we are. Then if I draw this in a 2D plot, I'm still in Lund, so we are somewhere there, but now it's flat. So that's just a different way of drawing the same thing. In the same way as when we draw the radiation pattern, sometimes we draw it in the spherical coordinates, similar to this globe, and sometimes we do it in this flat version. We would do both. And one thing that we can see there is then that the directions here, again, you have north pointing straight up, and then you have the other directions in some ways pointing here. That would be east in that case. So here you have north and east. And those are the same as you have on the globe, but on the globe they're turning around, and here they're only straight lines. One now important thing that you notice is that when you plot this in a different way, you can take one of these, for example, let's see, if you take one little square that sits there, let's take this one. That one then corresponds to, I'm not sure I will pick exactly the right one, this little square that sits there. Maybe it's not exactly the same, but similar one there. And then if I take one on the real Earth that sits there, then that one will correspond, so I'm not doing this completely wrong here, that one will probably be the one that sits there. So now you look at those. If you look now at the real Earth that sits upside here, what is the area of this one and what is the area of this one? Do they have the same area or do they have different area? I think you all agree that the area of this one up there is much smaller than the area of this one down here. But now if you look at this one, when we actually plotted them as longitude and latitude, the area is the same. It's two squares, they're exactly the same area. But of course, that's not the physical area. So when we plot this in different coordinates, the area looks different. In all integrals that we have when we should compute the total radiated power, there is a sine theta in those ones. That is due to this area change between this one and this one, which is this one and this one. Because they are the same in one of them, but in reality they are different. And there is a weighting factor there that we will see is sine theta. That will come up in almost all formulas that we have. So when we do it for antennas, as I said, this is exactly the same thing. Now, of course, I don't have the Earth drawn here. I just have a sphere. I put in my coordinate system. Now I measure it from the North Pole and down. That's my theta angle. And I have my phi angle that goes around here in this direction. It goes around here. That's my phi angle. And my theta angle is measured from there. And I can draw it here, as you did when you put your map on the wall. It has to be flat. And in the same way here, if you look at the area of these ones, yeah, that is one of them there. The area down here is much larger, but that's the area there. And I need this compensation factor again also in this case. So I need to do things when I go between these different coordinates. And if I now put in my directions, it means that I sit on the sphere, and we know that now our antenna is perpendicular to the radial direction. So it will be in two coordinates. One, I point now theta angle, increase theta, it goes down, increase phi, it goes around. So these are my theta and phi directions. If I draw it on the wall here, it points like this. One points straight down because theta is increasing when I go down. Phi is increasing to the right, so phi points to the right. That is my coordinate system when I draw this. And we can draw antennas in either of these two. That is just two different ways of plotting the radiated field. So the unit vectors here is in then the direction of increasing theta, which means when you close your eyes, look at it, it points south. So if you're here in Lund, it points not straight to Malmö, but in the direction of Malmö, basically. And if you put east, yeah, then it will go east, and that is the phi direction. So these are the direction that we are talking about when I say that the polarization will be in the theta phi direction. That is what is the direction of the E field. It's the same thing when you think about directions on Earth. And then different positions are where you are in the original theta and phi coordinate system. So these are the things that we have there. And yeah, phi hat in the increasing phi, which is east that we have. And as I mentioned before, we have this area change, that those things that sits up here is a very small area, down here is a large area, but in these coordinates here, they basically are the same. So when I integrate, I need to compensate for this. And we do that compensation all the time. So that is also an understanding of this. This is the map. So this is how they look when you then go to the formulas. And now this is one of the cases you should say basically thank you, because they are in the formula sheet. So this is formulas how we can go between a Cartesian coordinate system and a spherical coordinate system. We can jump between them. And there you should, of course, not derive this. We don't have to do it. We have them, but you should understand what they are doing. They go between these different directions at points in different points. So x is always in the x direction, but r hat can be basically in any direction. It depends on where theta and phi is. And that's what we use in antennas when we describe those. So to conclude all of these things, because now we basically have learned how we can go from a current density to a radiated field. What we do is that we write out this radiation vector, which is this formula, which you should remember as a Fourier transform of the current density. Then you change what you have inside of it, because here you can see it says an r hat. Yeah, then you need to plug in what is r hat. That was this spherical coordinate system. By doing that, you can compute this, that you need to plug in to compute what's happening in those cases. And then when you have computed it, you remove this radial component, and then you have the electric field. So that's a step you do. And that's a step we do in every case when we want to determine what the radiated field is from an antenna. It's not only something that I teach you here and we learn to do by paper and pen. When you use a computer that you will use FECO, FECO is doing that. So this is how we really compute the radiated field. Even in the computer is doing in the same way. So we can really get out the things from this analysis that we're doing. Okay, now I know we have quite some cover to do with dipole antennas. So now let's do the dipole antennas. Now we will apply this. So this I showed you before. These are two different dipole antennas. And now we will then compute what is the radiated field from a dipole antenna. I don't say what the length is of these ones. We will sometimes say it's a short dipole, which means it's short compared to the wavelengths. And sometimes it's a half wavelength dipole. And they behave slightly different. And sometimes it's a long dipole. It could be many wavelengths. But we will look at this structure. So what we need to do now is to compute this current density to the far field. So we need to write up that we have a straight wire dipole, and we need to write up what is a radiation vector, which means that what I have here is basically that I say first I have some current. It sits on a wire. We think that the wire is very thin. And then I should say, what is the current density? And then I need to write up what the current density is. And the current density only lives on the dipole. So one way of writing that is what I've been doing here. If you don't recognize the notation for this, I will explain it here. So it's point in the Z direction because the current here is moving like this. So it has to only move in the Z direction. The current cannot move here in an X direction. So I put that my wire is in the Z direction, which means the current flows in this direction. It doesn't flow like this because the wire is very thin. So that means I have my Z hat there. And then it only lives in the position X equal to 0, Y equal to 0, which means that I can plug in these delta Dirac distributions of functions. Those are 0 unless X is 0 and Y is 0. So there I can get my current density. And then it has some shape here in the Z direction. And it only lives over the length of this dipole. And I say that the dipole here has length L. So here I can write up what the current density is. Then I follow this formula that we got. I should compute the Fourier transform of this one. So I should take my current density. I should determine the Fourier transform. So we just need to plug it in. So I take this once, I plug it in there. And doing this, I need some space. So I'll just rewrite it on the new page there. And I then put in what is the source vector. So I have this part here, this r prime. I need to say what it is. And of course, I can write that in my Cartesian coordinate system. It has an x component, a y component, and z component. And this one exists there, and it exists there, and it basically exists there. So then I just plug them in, and to integrate over x, y, z, dv is the volume, that is dx, dy, dz. So this one goes straight there. And now I just took all of those things. So the J here is replaced here with one I had up there. And the piece I had here in the face, I plug in there. So I put in what is this R prime, basically what came from there. So this is what I should compute. I haven't computed anything else. I just took the formula and I plugged it in there. And now you need to integrate this. And you all have integrated these delta Diracs, which is the simplest function ever to integrate because the answer is 1. So we can do those integrations. So if I integrate this over x, x disappears. Integrate over y, y disappears. And I have to put in that x is equal to 0 and y is equal to 0, or x prime and y 0. So here I have to put in that these ones are those zeros. That was x, x prime and y prime, and now I cannot write x prime and y prime. That is what comes in there. And they are equal to 0, and that is due to this delta Diracs that I have here. So what I use there is this identity. If I integrate over the delta, I get 1. Integrate over y, I get 1. And if I weight it with the function, I get the function evaluated 0 in this case. And then I can plug in what this is, because of course here I had a lot of zeros, so I don't have to write up what the zeros are. 0 times x is 0. I only have something left in the z direction. And then I can take that piece and I can say that this part here of the r hat z hat that we had in the formula sheet before, of course now you don't remember it, but r hat times z hat is cosine theta. You can also see it if you see the coordinate system, because cosine or theta is the angle between r hat and z hat in these cases. And that means that this is what I have. So this is where I get out my radiation vector for this case. So it points in the z direction, and I have some weight over it here, which means I should take my current and I should weight it with this jk cosine theta z prime. And that's part that sits here in these ones. That was this time delay, that from the dipole, if I had the dipole here, sometimes I'm closer to the top and it's further away to the bottom. If I'm down here, it's closer to this point than this point. And that is what's compensated by this cosine theta and the z prime. And now I have to integrate that and sum it up, and I will know what my radiation vector is. So I can always, from a straight wire, write it as something here times z hat. So function f of theta times z hat. And for a specific case, I have to calculate what it is. So that is my radiation vector. And then I remove the transverse part of it. So I learned this right-hand rule. Take away the part that doesn't point in the r hat direction. So subtract that one, I take that away. And if I do that, I get that it points in the theta direction and it has some weight. And what you used here again was the formula sheet that said that z hat is equal to this. And this we can simplify a little bit because it's simpler to just write this up directly. This is by definition. And then I plug this in here. And what I do is that I take this away. So when I get the transverse part, just remove the radial part. And you have the same thing, just in a much simpler way. You don't have to subtract it. You can just delete it in some ways to get this transverse part. And that will be my radiation from this dipole. And then you get your electric and magnetic fields. And this is now general for any wire that points here in the z direction, and there is some current going on. Of course, to determine this Fz, I have to take and do the Fourier transform of Iz in some ways. I have to compute that. And that is what we will do now for a few important cases. So we will compute that for a few cases. If we do an interpretation again, so what I'm doing here is that I had my dipole here. It points in the z direction. If I compute my f, it still points in this direction. So that is my f. And I know that the electric field cannot have any component in this r hat direction. So I have to subtract that. And when I subtract that, I get this piece left here. And that is pointing in this theta hat direction, or minus theta hat direction. That is what I get out. And that is his right-hand rule. You have to take that away. Same if we were point in the x direction, we have to do exactly the same thing. It's just that then we remove the x direction, and then we get one component that's left again, because it cannot point in the r direction. And it's the same thing everywhere here. If I was looking in that point, then this r hat points there. If I'm sitting there, it's pointing in this direction, and r hat down here is pointing down. All of this direction is r hat, because r hat depends on theta and phi. It always points outwards. There's the normal direction to this sphere. Those are the pieces that we have to take away. Okay, so let's do that for our first dipole antenna. That is what we will use, and that's the simplest expression we have for an antenna to determine the directivity of an antenna. So now we do this for what's called a Hertzian dipole. And what is a Hertzian dipole? It is that I take this dipole antenna, and this is not now half a wavelength. I let the wavelengths here be really long. So the dimensions here of this dipole antenna is much shorter than the wavelengths. So it's just one current element that sits there and radiates. And that's called a Hertzian dipole. So what does that mean? It means that when I compute this, so I should compute this integral here, which comes from the Fourier transform. We can't compute it in these cases when the current in these cases is constant. So since this one is so short, we say that the current on this one is constant. And then I can just compute what's happening. And then I say here that KL is much less than 0. And then this one is just the current times the length. So that is my Fz. It doesn't depend on the angle. And if you think now, why is there no angular dependence on these ones? Why isn't any theta from this Hertzian dipole? What can the reason be? Because in the previous cases, I lectured so much about here that we have to know what the distance is from our antenna to the receiver point. And I'm interested in basically what the phase difference is from one point here to one point from here to the receiver. But what did I say here? I now said that the length of this one is much shorter than the wavelengths, which means that all points of these ones have the same phase. It doesn't mean that the current here have to have the same phase, but what it means that if I go over the distance here to the distance here, that is no difference in distance, because the length here is so short. So there is no phase difference in these cases. And that's specifically one for this Hertzian dipole. So that term disappears, and I can get out my electric and magnetic fields. I just plug in what I had. And now I can see here that I have my electric field. It points in the theta direction. So if you think about the sphere, it points south. It has an amplitude variation here. So the magnitude of this one depends on sine theta. So the dipole sits like this. It means that if theta is 0, the north pole, there is no electric field. The electric field is increasing until you go to 90 degrees, then sine theta is equal to 1, and then it starts to decrease again. And the same for the magnetic field, but it points in the phi direction. So that goes around this one. Imagine something that we might have seen before. If you have typically a current going in this one, current goes up and down, your magnetic field goes around it, which is this phi direction. So that is your electric and magnetic fields from this dipole. And this is how it looks. So this is the typical radiation from a Z-directed dipole. The electric field points in the same direction basically as the dipole, and the magnetic field is perpendicular to it. That is this phi direction and theta direction of that one. And then it's moving away from your dipole. That is how it looks, the radiation from it. And this is in a 2D plot. So you have very strong fields close to the center. Your dipole sits here, and you can see that I took away even the color scale close to it because it's singular. So it's very, very strong fields close to the center of it. That is this reactive near field that's pumping. And then the field decays when you go out, and the field decays as 1 over r when the distance increases. And there are small errors in these ones. They might be hard to see. They point in the direction of the electric field, and they goes in the theta direction. When you take the magnetic field here, it goes in the phi direction, so there is no errors on all of those. That's always just inside or outside of the plane that we see. That is how the magnetic field points. And now I compensate of these ones because I said that the decay is singular in the center and it decays as 1 over r. So let's weight the electric field with the radial distance. It's easier to just see what it is, because now you can see that the amplitude of the electric field and the magnetic field don't decay anymore because I removed the decay. And now you can see the directions of the electric and magnetic fields. So if you look inside here, if I stop this once here at one instant, and maybe let's stop that one so we don't have to see it. Here you can see, if you look at the arrows here, you can see they float around here. And that is this theta direction. That's how you measure your theta angle. And you can see that the arrows point in that direction. If I look here, you can also see they point in the theta direction, but in the opposite direction. It's still the theta direction, but because we have a phase on this one, so it's just that one is +1 and one is -1. When you sit inside here, you can see that the field points in all kind of weird directions. That is this reactive field. Because here it's not only the far field. This is the full field that is calculated in this case. So that's how the field looks like. If we look at the power flow, so what is the power going from this dipole? Here we can look at the real part of it, which is the active power flow, which is really the one that propagates something. And you can see that all arrows basically point outwards here. They go always away from the antenna. So the power tries to disappear from the antenna. You can see up here it's equal to 0, and down here it's its max in some ways. When you look at the reactive power flow, you can see it goes around the antenna. The reactive power flow doesn't really push away any energy, it's just energy that's flowing around the structure. That is the thing that you have if you put something close to you. It's a very complicated structure very close to your antenna. It can interact in all ways, and that is the near field. In the far field, and this time average power flow is the one that we care about, and that's what dominates. This one here, the reactive one, decays very rapidly. So it disappears in those cases. And we get radiating outwards here. If we're now going to plot this and we're going to determine what it is, because that's what you're going to learn how to do, the other ones we can do in MATLAB. Yeah, we take our power density. We computed before, E cross H, and we've shown before that that is this radiation vector, the orthogonal component of it squared. It's a huge constant here. When it comes to the constant, you say thank you, because that's in the formula sheet. It's kind of hard to memorize that one. You don't have to do it, it's in the formula sheet. But the pieces that sits outside of this one, these ones are very important. And those you should know. You should know it propagates away from the antenna, and you should know that the amplitude is the radiation vector squared, or the orthogonal component of that one squared. So that is the radiation intensity. That's what we can get out. And then we need to see what this looks like. And then we plot it in different ways. And a typical way is what comes here. And now we will show how we can determine this shape for this dipole, because this is the shape we will get for that one. We haven't computed it yet. We will do it now. So take the radiation intensity, you plug in the Hertzian dipole, and you get an angular distribution here, which is sine square theta. And then we should compute the total radiated power, which means that we have the radiation intensity, how much goes out from the sphere. I need to integrate that now over the sphere, and that is sine theta d theta d phi. Again, do you remember what the sine theta was? Yes, that was this small area at the North Pole that you have to compensate for. Because when you integrate over the theta d phi, that is on this map that you put on the wall. That's a Cartesian coordinate system for that. But you should integrate it in the spherical one. And when you go between those, you have to compensate for this area change. That's sine theta. North Pole is small. Equator is very long around the Earth in some ways. And doing this, we plug in the formulas. You get sine 3 theta there. You all can integrate that. If you've forgotten how to do it, you can go to the formula sheet. It's in the formula sheet. And plugging this out, you get a very long formula. doesn't matter what the formula is here, you can compute it. But now we should have the directivity. And what was the directivity? That was the radiation intensity normalized with the total radiated power and 4 pi. So basically the average radiation intensity. And that means you should take the quotient between these two numbers. You can see here that everything there disappears against basically everything that sits there. And if you do that, you get out here the directivity. And the directivity in this case is now a very simple formula. That is the directivity for any short antenna or small antenna, electrically small antenna. Here the Hertzian dipole, of course, it's infinitely small, so we can easily compute it. But everything that gets really small in terms of wavelengths will look like that. Because if it's very small, you don't really have any phase difference inside of it. Or, I mean, you can always try to build it, but it gets increasingly harder to do it when you make the antenna smaller and smaller. And then we plot this. And if you plot this function, you can see you have this sine square theta. So the maximum value is at 90 degrees, and there the value is 1.5. If you go to 60 degrees, so you go to this angle, then you have a value here, and that you can take by taking sine squared of theta times 3.2, you get the value. And the further north you go on this, it goes down and gets weaker and weaker. And this is how we plot the radiation pattern. We typically plot it in a polar coordinate system. So this is how it looks. And that is the intuition of it. And then this pattern in this case is independent of phi, just a second. And that means that we can plot it in a 3D way, and then we rotate this around. And if you're hungry now after lecture, it looks like a donut. So when you think about the radiation pattern for a short dipole, think like a donut. It's what it looks like. And the maximum value is 1.5. That is given, and that is the smallest electrical charge that source that can radiate. Okay, there was one question here. I didn't see the name.
Yes, Khaled.
Yeah.
Actually, I didn't understand how did you calculate the radiated power?
Can you say it one more time?
How did you calculate the radiated power?
How I get the total radiated power here?
Yes.
Yeah, so if you think about this, the radiation intensity, say how much is the power in a certain angle. So the radiation intensity here is something that says what is the radiated power in the angle theta and phi. It is the power per angle in some ways. And then to get the total power, you have to sum it up over all directions. Because the dipole here you have, it radiates in this direction, this direction, this direction. I have to collect all of that radiation.
Okay.
So I integrate it over the huge sphere that sits around these ones. If you make the picture with the Earth as I had before, what you do is that you put your antenna in the center, and then you collect all the radiation that would come out from the surface of the Earth. Of course, Earth is empty now, but assume you can sit on the top of it. You get the power everywhere. And then you sum all of that power, but you also weight it with the area where you measured it over. And then you collect that over the entire Earth. That is the total power that has radiated from the antenna. So the integration that I do here, you can see it is over theta and phi. Theta goes from North Pole, 0, to the South Pole, which is pi. Phi goes around the structure, for example, around the equator. Then it goes from 0 to 2 pi. And then you had this little weight sine theta that comes in. So that is the total radiated power, because the power that's radiated have to escape this sphere. And I have to sum it up.
Yes, but why sine theta here?
Why this sine theta? This one.
Yes.
Yes. Well, let's go back to it. Because that sine theta is very important. And it always shows up, and I know it's always confusing. But here, so when I do sum this total radiated power, I will get some power that goes out through this little region here. When I integrate it, I basically integrate it here. The height of this one is d theta. The width is d phi. That is the length there, and this one here. Those are d theta, d phi. So this one here is d theta, and this one is d phi. So I could sum up this rectangle as I have here by taking the base times the height. It's a rectangle. But now look, then we go up to the next one here. So instead I go to this one. D theta and d phi are exactly the same thing. But that one is sitting up here. And look at your sphere. So if you think about Earth, your globe, what is this size of this little element up there compared to the big one that sits below it? So how big is this one compared to this one? With your eyes, you can see the red one here is much larger than the blue one. And the compensation between going from there to compensate for this area change is exactly sine theta. That is that compensation. So it comes because I jump between the spherical coordinates to write this in theta and phi and integrate over them. I'm actually integrating over Cartesian theta and phi coordinate system. But I should integrate over a sphere. And I need to compensate for that. And compensation is sine theta. That's the one that sits there.
Thank you very much.
Here I'm just claiming that this is the case, but that is what you have done before in math courses. Typical multi-dimensional analysis courses. So that's a compensation that sits between those two. Is that okay for everybody? You will come back to it in exercises because there are many exercises in this direction. Okay, we should move on a little bit with this dipole because the Hertzian dipole is a really good thing because we can understand it really well. Okay, so here we had then the directivity of these ones. We can then say that what are the receiving properties of these ones? We will also look back at this. We went through this last week or last lecture when we look at the relationship here between the effective area and the gain of the antenna. And you can see it scales with the lambda squared times the gain. And then you can ask, what is the effective area of these ones? If we had a big parabolic reflector, we would believe effective area is maybe the physical area. But what is the effective area of a Hertzian dipole? So then we can compute it. So we take the formula. Let's assume it's lossless. So let's assume it's perfectly matched and lossless. Then we can plug in here that instead of the directivity, we can plug in, or in the formula instead of the gain, we can plug in the directivity. And we can actually see here that in this case, the area is 3.75 lambda squared. What is surprising with this? It doesn't depend on the length of the dipole. So if you assume you have a parabolic reflector, you receive a signal, basically every photon that hits it, it's like particles, this electromagnetic field, would be received. But now you have your tiny, tiny antenna, which is like 1/100th of a wavelength. It still receives a photon that comes here. It's missing the antenna, but somewhere it gets sucked up into it. So in some ways, this perfectly matched small antenna has a size of 0.35 wavelengths times 0.35 wavelengths, and it basically collects everything that comes inside of that. And that is something that's happening when you go for a small antenna compared to a large antenna in these cases. So they can have some very mysterious properties in this ones. Okay, we don't have so many minutes left, but I will also show you the half-wave dipole in these cases. So when we increase the length of the dipole, so I take my dipole here and I say it's not very short, it may be half a wavelength, maybe it's longer. When I have this lambda here is 2L, that's called a half-wave dipole. That is the perfect dipole. That's where we want to be. We will next lecture see that it's actually slightly off from that. If I do the short one here, the current looks like this. And if I make it longer, it starts to oscillate. And a very good approximate formula to that is actually some sine function for this. So this is just heuristic, that it approximately looks like this. And if it's small, it looks like this triangle that we said there. So this is a typical short one. That's it. And now if we would like to compute this, and if I want to compute my radiation vector, They are computed here, and you can look at it in the appendix. It's all of these dots. If you compute this, you can actually get it out there. So that says if you have this radiation pattern, you can compute the radiation vector out of it. So you can get that out. And now we can a little bit try to understand what's happening when we look at some properties of this. I will end in like 3 minutes or something. And if we make it short again, yeah, we get the Hertzian dipole back. But when we look at these ones, if you now can see that when you have a current here that starts to oscillate, so look at the green curve here, this is how your radiation pattern looks like. When you have the shorter ones here, I actually think the blue and red unfortunately are mixed in these cases, but you can see that looks like this dipole case we had before, this donut. And the reason for that is that if you think about the current up here, the blue and red, they have the same phase everywhere. And if the current has no really changed phase, change of its phase, and the length of this dipole is small, then the phase from different positions will not really change a lot. But in the green one here, you can see that sometimes this you can see is larger than 0, and if you go in this direction, it's less than 0. So the current is sometimes positive, sometimes negative. That's 180 degrees phase shift. And it's also long in terms of these ones. And now you can get a very strange radiation pattern. So the radiation pattern of your antenna depends basically how complicated your current can be on your structure, and then the distance from different pieces and what that phase difference is. And when the antenna is small, not much can happen. But the antenna gets longer, a lot of odd things can happen. And that creates a radiation pattern that is start changing. We will see much more about that later in the course. And this is again then the same way of plotting it. So we can plot the directivity here. You can see here, this is the max. It's easy to see at 135 degrees. That means it is this direction. So when you look at these polar plots and the Cartesian plots, you can compare how they radiate, and you need to be able to understand what these plots actually depict in these cases. And now we come to the perfect antenna, and that is the half-wave dipole. So from that one, we can also determine what the radiation vector is. It actually looks like this. And then from that, we can compute the directivity. It can be done, but it's incredibly difficult to do. It's fairly easy to do numerically. And what you see in that case is the directivity of a half-wave dipole is like 1.64. So slightly higher than your Hertzian dipole, but not much. The difference is not big. So in the first approximation, you can just think about the Hertzian dipole and the donut shape. And when you go to the half wavelengths one, you can see it's slightly above 1.5. So a little bit, think about your donut and you press it down a little bit and it gets a little bit longer in one direction. That is the radiation for a half-wave dipole. And on Monday, we will talk a lot about half-wave dipoles, because then we'll talk about resonances for these antennas. And a typical example, this sleeved dipole, and we can compute the length of it, and we can see that F0 is around 1 gigahertz of this, but actually in cases here, we will see next lecture that it's slightly shorter, and actually this is resonant at 900 megahertz, and it's actually an antenna that is made basically from the first, 2G type standard antennas for cellular communication, where we only had a 900 megahertz band in those first cases. We will skip this one for today. We could have an idea what the current is. We will come back to that too. And with that, we actually end it today, because I have to quickly show you the quiz too. Just for next week, also FECO is coming up. So you can get download FECO, and what I need to do is basically to send your information to FECO if you would like to use FECO. So all of you who would like to have FECO, I will set it up on Canvas, so you can just sign up to say I would like to do it, and I will send the information so you get the correct license files from them. I will write that on Canvas. And it's good if you can do that, say, before Friday. which is tomorrow. So I will put it up on Canvas, and then tomorrow afternoon I can send it to FECO, and then you will be able to have it before the computer exercise on Wednesday next week. You can also run it in our labs on the 4th floor, but it's best if you can do it on your own computer. And that's a very good software. So with that, I will quickly also show you we can stop the recording.